Hello everyone, hope you are all doing well. Here in this video we are going to learn how to design a PID controller which is optimally working and is designed by COA optimization algorithm to control any plant, but here in this experiment we will control a DC motor with a PID controller designed through an optimization algorithm called COA optimization algorithm. For this I need to open both of these files. The first one is the cost function, the second one is the optimizer algorithm. So we open up those two files here. As you see on our COA main, or the optimization algorithm code, we have added some lines of code up here. We have defined some steps. We have defined simulation time 10 seconds. We have built our simulation vector, our simulation time vector. We have defined S as transfer function parameter, and then we have defined our model, which is open loop system. Here we have used a DC motor. We define our cost function here. We have three parameters to optimize, which are coefficients of a PID. Three coefficients needs to be optimized. We have to define some lower and higher bound for searching these parameters. This is not something predefined in the program. You have to do some trial and error to find the best value maybe, but I have chosen -2 and 20, which seems good enough for this simulation. Number of cuckoos, I've used 5. Minimum number of eggs they lay is 2, and the maximum number of eggs each of them lays is 10. Number of iterations for the optimization is selected as 10, and I don't need any other parameter to change and consider here. In our cost function, we have a candidate matrix for PID parameters. I separated each column of this matrix as KP proportional parameters, KI integral parameter, and KD as the third column for differential parameters. Then I have built for each row of this entering matrix, I've built a controller based on these KP, KI, and KDs. Then I have sent that controller to feedback command of MATLAB, multiplying by open loop system and saying to MATLAB that that's a unit feedback. Then I get the closed loop system here, and using that closed loop system as an input for step function of MATLAB and sending the time vector for simulation, I can get Y as MATLAB's output for this simulation. Then we have to assess this output signal and build our cost function and calculate our cost function if I need to be more detailed. I have said that if the absolute value of this output signal Y is bigger than 10, then we assume it as unstable system. So we put a big value for cost of that row. It means that this controller for this iteration is a non-stable system. So we can omit it by punishing optimizer algorithm, which through a big cost value here. Otherwise, we can find the difference of output signal Y with the ideal signal which is step, unit step, and it can be considered as 1. And summing and adding up all these points through simulation time here, we can get our cost value. We need the output to be the most similar to our input signal, which is a unit step. So we go back here to the main function and start to run the code, and we will wait a little for COA optimization algorithm to finish its simulation and give us some result for this PID control application. We will compare the results with Ziegler-Nichols as a classic method, and you already know that we have to run the optimization algorithms over and over because they trap in local minima most of the times. So optimizing the algorithm will produce best result in a couple of iterations. But here, as you see, COA has produced much better result compared with this Ziegler-Nichols. This black line is a Ziegler-Nichols method, which has a overshoot, and then it fluctuates a little over around 1 and then settles down. But the controller which COA has proposed us moves much faster. It has better rise time compared to Ziegler-Nichols, and it really avoids the overshoot here, which is caused by Ziegler-Nichols method. So as you see, we can have better performance using COA optimization algorithm even in a simple DC motor control, which is done through PID parameters. If you want the best P, best I, and best D parameters, you can see them here. Overall cost is shown here, simulation time 44 seconds on my system, of course. And that's all. You have a optimal controller for your DC motor here. Hope you can use this code for your own applications and get better results than any classic method there.